Monday, right? Like, so till probably what we covered till last class. Okay. Uh, all right. So let's start. So right now we are moving into the circuit design part. So till now we have been looking at how we can, what are the different parameters, the performance metrics that we use to characterize different RF, right? And what are the ways in which what are the metrics, how do we compare them, how do we derive them, and all these things we have looked at. We also looked at some impedance transformation networks and so on. So we got some idea about the passive networks, how they behave, resonance behavior, and so on, right? So now let's, and we also looked at some device behavior and looked at how we can, you know, how does the device behave, how do we, use the device and so on. So now we are going to move into how to actually design an LNA. So now what we're going to do is basically to go step by step and then build up an LNA. Okay. Now there are different types of LNAs. In fact, the textbook itself covers quite a few types. What is there in the textbook, most of them will be seeing. But based on these types, okay, there are so many different LNAs that are being designed and being used, most likely in your cell phones and so on. Okay, all right. So let us start with a very simple thing, which is basically to say, okay, all of you are familiar with what is called as a common source amplifier, right? So what is a common source amplifier? Just like how you have a common emitter amplifier, you have a common source amplifier in the CMOS domain. So you have a certain VDD. Let's say this is your transistor M1, okay, and you have your input is given at the gate and the output is taken at the drain. Okay. Now in last class we saw what is going to be the input impedance of this, right? Or rather we looked at what is called as the Y-in, right? What is the input admittance, and we saw that the input admittance is a function of, you have a real part and the imaginary part, and the real part is a function of the frequency, and the imaginary part is also obviously a function of the frequency. Okay, and we saw that if you look at a real part of Y-in, the whole inverse, which is nothing but the real part of, okay, it's not exactly the real part of Zn, but then what is the real part of the impedance looking in? Okay, we saw that this is much greater than 50 ohm. All right. So what happens is, immediately the question is, why not put a 50 ohm, right? So all you need is basically you need a 50 ohm input impedance, and we see that this impedance looking in here at, let's say, our around 1 gigahertz or the lower gigahertz frequencies is very large, probably in the kilo ohms range. So why not just put a 50 ohm resistor, right? And let's say maybe you can have an inductor to tune out the capacitance that is there. Okay, so let me just say there is a parasitic capacitance sitting here. Okay, so if you do this, you should basically, if you look from here, let's say Zn should be nominally 50 ohm. Okay, so this seems to be a fairly good idea, because as I mentioned in last class, the primary problem is to make sure that the input impedance is 50 ohm. Okay, that's when your S11 will be quite good. That is, it will, if you look at the Smith chart, the impedance will be close to the center of your Smith chart, the 1,0 point, right? And if you look at the magnitude plot, you'll have a nice proper dip at the frequency of interest, right? Okay, so let me, if this is the Smith chart, okay, this being the center of the Smith chart, okay, this is basically your 50,0 point, right? So you want to be here, and if you look at the, let's say your curve is, something, it might be something like this, something like this. So let's say at this frequency point, it is basically going to be at 50 ohm. Now what can also happen is you can also look at it in the magnitude plot. Okay, so let's say this is the frequency axis, and let's say this is 20 log of S11. Okay, so what you would see is basically that it will become negative at the frequency of interest. In fact, it will be negative. Okay, it should not be positive. Okay, and if your 20 log of S11 or 20 log of S22 is positive, it means that the system is unstable. I think this you would have learned in your microwave circuits course, right? So S11 and S22 have to be negative in the logarithmic domain, and in real numbers it has to be lesser than 1, right? That is to say that if you are sending some amount of power, the reflected power should be less than, I mean, the ratio of the reflected voltage and the incident voltage should be basically less than 1. Okay. If the reflected voltage is greater than the incident voltage, then it means that the circuit is oscillating and it's generating signals on its own, right? So that is the problem. So that is why S11 and S22 have to be less than 1, and in the logarithmic scale they have to be less than 0 dB. Okay. Now usually what happens is, if you when your input is properly matched, the incident wave or the incident power is fully absorbed by your system. Okay, so the reflected power is very, very less, which is why you get a very deep negative point at the frequency at which you have matched your LNA. Okay, all right. So now what we are saying is, we are using this LS to take care of the reactive part, and we are putting a 50 ohm impedance to take care of the real part. Okay, let me just call it as RP. So let me redraw this circuit, and let's see what will be the noise figure of this circuit. Okay, so this is V in. Let's say this is the source resistance. Okay, let's say this is, I mean, you might basically include a DC block cap also, because you don't want, or sometimes the DC block can be on the other side also to bias the transistor. Okay. Okay, let me not complicate with those things. Let's just stick with this. Okay, and okay, let me call it as RP. Okay, there is some LS. All right. So now what we want to do is basically to see what is the noise figure of the system. So before we look at the noise figure of the system, we also need to look at what is the gain of the system. Okay. Now what is the gain of the system? First of all, the voltage at this point, let me call it as voltage point X. Okay. What is the voltage at this point X? We can say V in into Rp divided by Rp plus Rs. Okay. Assuming that the inductor and the capacitor are tuning out each other. So for all practical purposes, for our analysis, let's just say that we are left with this. Okay. Now what is happening here is, you have Rp divided by Rp plus Rs. Okay. Now what is the gain of this system? So let us draw the small signal equivalent circuit. So what is the small signal equivalent circuit? We have a dependent current source, Gm times Vgs. Let's not draw an R0, or let me just draw R0, and anyway we will take care of this. Okay. So this is the source node. What is the source? What is connected to the source? The source is connected to ground, right? So let's say this is grounded, and then you basically have Vx here. Okay. Vx, which is nothing but V in times Rp divided by Rp plus Rs. All right. So if you want, I can basically draw it as this. Okay. And then we have Rd connected from this point to VDD. So a DC supply is taken to be an AC ground. So this is a small signal circuit, so we just connect it to ground. Okay, so this is our V out. All right. So what we are going to do is, so here if you see, usually R naught is much greater than RD. So you can basically approximate R naught parallel to RD to be equal to RD. Okay. So what is V out? V out can be written as what? There is a current source which is flowing through, which is pulling current through the parallel combination of these two resistors. So V out can be written as minus, because of the direction of the current, right? Gm VGS times R naught parallel to RD, right? And this can be written as minus Gm VGS RD, approximately. Now what is VGS? So Vx is nothing but VGS, right? So VGS we have already, this is nothing but VGS. So V out can be written as V in times Rp by Rs, Rp by Rp plus Rs into Gm times Rd. So what is the gain? V out by V in is the gain, and so AV can be written as Gm times Rd into Rp divided by Rp plus Rs. Alright. This is your voltage gain from input to output. Okay. Now let us look at noise. So for noise, what do? We set V in to be 0. Okay. So what do you get? You have Rs here, and you have Rp here, and then you have the transistor here. Now the transistor basically has a noise current which is given by 4 kT gamma Gm, and you have a resistor here. Okay. The resistors, yeah. The noise of the resistor is basically can be taken as 4 kT Rd, right? This is our V out. Okay. Now what is the thing? So this, now what do you have? So basically you have Rs and Rp in parallel, correct? Now what is their noise contribution? Their noise contribution can be taken as a series noise voltage source, okay, whose value is 4 kT Rp parallel to Rs. Okay. Now what we have to do is Vn out. What we are interested in, Vn out square bar. Okay. So all these terms are, remember, noise power spectral density. Okay, which means they are per unit frequency, per 1 Hz bandwidth. Okay, and this is the noise power spectral density, and this is, all this is thermal noise. Okay, right now we are not talking about flicker noise. Okay, so what is Vn out squared? So we, by superposition, what we can do is, so all these noise sources are uncorrelated. Okay, so all these noise sources are uncorrelated, so we can directly add their power at the output. Okay, so for 4 kT Rd, what happens? That directly happens to come at the output. Okay, so one way to look at it is to say that, by superposition, this is how it is, and then the output is basically 4 kT Rd. You can also say that it is a parallel current source with 4 kT divided by Rd, okay, multiplied by the output resistance. So output resistance R out is basically Rd. Okay. Now if you want a proof as to how you do this R out equal to Rd, I'll just take you back to this particular thing. Okay. Let me just put it as an aside to find the output impedance, right? What you can do is set V into 0 and then connect a test voltage source at the output and measure or calculate, let me just say calculate, the current through it, IT. So Vt by IT becomes the R out. So in this case, okay, let's say, let me use a different color. If you put a test voltage source here and you set V into 0, what happens? VGS goes to 0, which means this becomes an open circuit. Okay, Vt by IT, what is the current drawn here? Vt divided by R naught parallel to Rd, which is approximately equal to Vt by Rd. So VT by IT is nothing but RD. Okay, so that's how we get the output impedance to be RD. So you can calculate the resistor output noise to be like, you get the output voltage, the output, you can take it as the noise power spectral density multiplied by R out squared. So there you will get the same thing. Okay. Now this plus, let's look at the device noise. Okay. So the device noise is the current. Okay. 4 kT gamma gm is the current, but we want the voltage. What is the voltage? Output current multiplied by the impedance squared or R out squared. So you basically get gm RD squared, 4 kT gamma gm RD squared. Okay. So remember we saw in the earlier classes, just I want to bring to your memory that we said that for noise power spectral densities, we multiply the quantities with the square of the transfer function. So here the transfer function is the resistance, right? You have a certain amount of current which is being, pulled from the output, and what is the output impedance you calculate, and GM 4 kT, if there is a current, you will say, the MOSFET current into RD is the voltage, okay? But for the power spectral density, you will say the current power spectral density multiplied by the R out squared. So that's how you get 4 kT gamma GM into RD squared plus, what do we have? We have 4 kT RP parallel to RS. This is the noise voltage power spectral density at the input. So this multiplied by the transfer function. What is the transfer function? It is the gain, the intrinsic gain of this device, which happens to be GM RD whole square. Okay. So this is your total noise at the output. 4 kT RD plus 4 kT gamma GM into RD square plus 4 kT RP parallel to RS into GM RD the whole square. Okay. Now we need to find the noise figure. Okay. What is the noise figure? Noise figure can be given by total noise at the output divided by gain squared into 4 kT RS. Right. This is our basic noise figure equation. Okay. So what is the total noise at the output? We said 4 kT RD plus 4 kT gamma GM RD squared plus 4 kT RP parallel to RS into GM RD the whole square divided by, what is the gain? Gain is RP by RP plus RS the whole squared GM RD whole squared into 4 kT RS. So the rest is just simplification. So I would encourage you to work it out. Okay. So at the first shot, 4 kT will cancel out in both the numerator and denominator, right? So, and if you expand it, you will basically get 1 plus RP, RS by RP, okay, gamma times RS divided by GM RS parallel to RP the whole square plus RS divided by GM squared RD into RP parallel to RS the whole square. Okay. So because since the point of the class is to go beyond the equations and to look at the actual thing, I want you to work them out. It is simple arithmetic. Okay, sorry, simple algebra. So please do that. Okay. So if you just simplify, you basically get this. All right. Now looking at this expression, can you tell me what will be the minimum value of the noise figure? So RS is 50 ohm, RP is also 50 ohm, right? So if you do some substitutions, okay, let me say this is basically going to be 1 plus RP is also 50 ohm, RS is also 50 ohm, 1 plus gamma is close to 1, okay, gamma is close to 1, and then you have certain terms, okay. So we can very confidently say that noise figure is going to be definitely greater than 2, right? In fact, it can be substantially higher than 2, but definitely noise figure is going to be greater than 2. Okay, that's definitely the lower bound limit. Okay, so for a noise figure greater than 2, it basically means that noise figure is greater than 3 dB. Alright. So noise figure of 3 dB once you know, in the logarithmic scale, which is quite a high value. Okay. We want to design an LNA whose noise figure is not so high. In fact, the noise figure of this will be much higher because the other two terms, okay, let's say GM times 50 will be some, you know, something like 1 or 2, I mean, again, GM times RS parallel to RP, okay, you have squared. So probably it will be around 10 or 15 maximum, okay. And because RS is only 50 ohm, so you will basically have a fairly large amount of noise figure. Okay. So while this LNA that we looked at, okay, seemed to be a very attractive one, it's a very straightforward one. All you do is just from first principles you try to do. The unfortunate thing is its noise figure is quite high. So you can no longer call it as a low noise amplifier. It can work as a normal amplifier whose noise figure is, let's say, some 4 or 5 dB. Okay. But that is definitely not qualified as a low noise amplifier. Okay. So now we need to come up with techniques where the noise figure can go lower than 3 dB. Okay. So how to, at the same time, we also need to do what? We need to match the input. Okay. So somehow we need to match the input. All right. So let us look at one more circuit today. Okay. But before we go into that circuit, I want to talk about one more type of circuit. Of course, so basically nobody uses this topology for an LNA. Okay, you can basically use it for an amplifier where the noise figure is really not important. Okay, now I mentioned that we are going to put RD here. Okay, I want to look at the output side first. Okay, I just want to take a look at it. Now this LNA is going to get connected to some other circuits. Okay, so effectively, as I kept mentioning, you will have a certain load capacitance at the output. Okay, now the output impedance is RD. Okay, now if you add the CL, what happens to your small signal equivalent circuit? Let me just quickly draw. You have, let's say, RD and you have a CL. Okay, so now what happens? Your Vout is nothing but minus GM VGS times the value of this current source is GM VGS times RD parallel to 1 by SCL, right? So if you evaluate this, what will you get? You will have minus GM VGS RD divided by 1 plus S times RD CL. Okay. So this is a typical low pass filter response, right? You have a pole at 1 by RD CL, correct? And a single pole system. This is obviously a low pass network. Okay. As frequency goes up, the gain is going to come down. Okay. So any amplifier is basically a low pass network. Okay. If you don't use inductors. Okay. So what we need to do, so for example, the low pass nature, depending on the value of RD and CL, the corner frequency can be maybe 100 megahertz or 200 megahertz. Okay. Depends. Alright, but if you want to design a low noise amplifier at, let's say, 1 gigahertz or 5 gigahertz or 10 gigahertz, obviously you are in the low pass regime. Okay, your F is much greater than the corner frequency. So this topology is definitely not going to work. Okay, so what can we do? We need to make this into a tuned amplifier. Okay, so you can again go back and try to reduce the value of RD. Now, if you reduce the value of RD, what will happen? Your pole frequency will increase, but your gain will start coming down. Okay, so that's really not the way to go about. So you have to put an inductor. Okay, so we transform this into a tuned network, right? By putting an inductor. Okay, so which is why you will see that most of the RF systems will have some inductors or the other. Okay, now when you have an inductor, what happens? The small signal circuit becomes like this, right? You have GM VGS, which is your current. Let's say you have L and you have CL. Okay. Now, what we can do is this inductor obviously is not an ideal inductor. I think in one of the previous classes I talked about the parasitic model of the inductor and so on. Okay, but a very simplified model of the inductor can be that inductor with the series resistance RS. Okay, now you can also transform this to L with the shunt resistance. Correct. And we know how to do this. Series parallel transformation, we know how to do this. We have looked at, Rp will be Rs into Q squared plus 1, right? We have done that in one of the previous lectures. So these are mathematically equivalent circuits. So what you can do is you can model this inductor, okay, as a inductor with a shunt Rp, okay. So this Rp is basically going to model the loss of the inductor and even the capacitor. Okay, so all the loss is kind of modeled and thrown as a shunt resistance. So what you will have, you will basically have something like this. Now what is this? It's an RLC network. Okay, so V out can be written as minus, V out basically, let's say V out is here. V out can be written as minus GM times VGS, divided by, let's say, the Y equivalent. Okay, where Y equivalent is nothing but the parallel combination, the admittance of L, CL and RP. Okay, the parallel admittance. Okay, so basically it's a simple parallel RLC network. We know how the RLC network behaves. So if you design the value of inductor L such that it tunes out the total capacitance at this output node. Okay, this total capacitance at this output node, as I mentioned, consists of the CdB of this transistor M1. Okay, and also, you would have studied about Miller approximation, so CGD will also come, plus the input capacitance of the next stage. So the total amount of capacitance at that output node has to be tuned out by this L such that it becomes a resonant network. Okay, so now your transfer function will look like how? Let's say this is your F, it will basically look like your parallel RLC network. Okay, so the gain of the system, let's say AV, is going to basically look like something like this, where this is your frequency of interest. Alright, so now what is of interest is when you have an inductive load, okay, let's say it has a certain Rp and let's say you have a effective CL here, okay, and let's say you have CGD here, you have CGS here, okay, and if you take a device which is looking like this, what is its input impedance? Alright, so in last class we took a resistive load and we computed the input impedance and we had a very big term, okay, and we said that this big term is quite high, and therefore we thought we'll put a resistor at the input Rp, which is 50 ohm, and then try to design an LNA. So now I am throwing another problem into this whole mess and say that if you put an RD, basically if you have a resistor, it's going to have a low pass response, and therefore you cannot use it for very high frequencies. Maybe for VHF, UHF range you can still manage to use it, but for very high frequencies you cannot use it. Let's say for 1 gigahertz and in the gigahertz range you cannot use it. So we said the solution is to put an inductor and make it a tuned network at the output, right? So with a tuned network, what is going to be your input impedance? So that is what we are going to look at. So how will you do that? You basically draw the small signal equivalent circuit. You say, okay, this is my CGS and I have a CGD, right? And I have, a current source GM VGS, where VGS is defined as the voltage across this, right? And then you basically have an L and you have CL and you have RP, okay? Now what we are interested in is what is for this network, okay, source is grounded, what is going to be your Yin or what is going to be your Zn, okay? So again, obviously from looking at the network, we know that this is a very messy network. So thankfully there are people who have already done it, okay, and we will just look at the results. Okay, what is important is basically what is the end result of the derivation. Okay, so the end result of the derivation turned to be something like this. The real part of Zn is going to look something like this: Gm times L squared C CL plus CGD omega squared plus Rs into 1 plus Gm Rs. Okay, so here I think they have taken okay, so there they have taken it as a series resistance. Okay, they have not modeled it as a parallel resistance. You can do either way. Okay, CGD plus CL minus Rs CL plus GML divided by some big term. Okay. Now, what is interesting here is, in contrast to the previous expression that we wrote in the last class, where the numerator was entirely positive, both the numerator and denominator, the entire term was only positive. Okay. It turns out that in the numerator of this particular expression, there is a negative term. Okay. And this denominator is always greater than 0. Sorry, not 1. Always greater than 0. Okay. So denominator is positive. So looking at this expression, we know that there is some point at which this real part of the input impedance can go below 0. Okay. So what we are saying is, there exists some frequency omega, let's say omega 1, which is given by rearranging all these things, okay, which works out to be something like this: 1 plus GMRS Rs into CL plus CGD divided by GML squared into CGD plus CL. CL. Okay. So you don't need to mug up or memorize all these things. These are just for us to understand. Okay. So this is the frequency where the real part of Zn becomes negative. Okay. Now, what will happen if your input impedance becomes negative? Can you answer? What can possibly happen? Anybody? You have some circuit, the input impedance becomes negative. Okay. Where have you used negative resistance? Where have you seen negative resistance?
Diodes, sir.
Diodes, typically, which type of diode?
So I forgot the name. There was some diode, gun diode actually. Gun diode.
Tunnel diodes, right? Some of these. So where are they used for? The negative resistance is used where? To build what type of circuits?
Oscillators.
Oscillator, exactly. Okay. So what you will do in an oscillator is basically, like if you recall your oscillators, what you would have learnt in your analog electronics and other things, the negative resistance cancels out the loss in the tank circuit, right? And you will basically get an oscillator, right? Now here again, what are you having? You are having a negative impedance, and therefore there is potential instability. We say there is potential instability. Now what is instability? In electronic circuits, instability basically means that the amplifier starts to oscillate. Okay. Now that you have negative impedance, negative resistance at the input, if because of some stray, inductance, capacitance which are there, because once you do layout and other things, there will be some parasitic components coming along, right? It can just basically start to oscillate at some frequency, okay, which is given by the effective L and C of the whole network. Okay. So which is what we call as potential instability. Okay. So this is something very, very bad. You really don't want this to happen. Okay. So you want your amplifiers to amplify. You don't want your amplifiers to become oscillators. If it becomes oscillator, then there's no point. No, let's say you're giving let's say you're receiving some signal from your base station. Okay. You want your LNA to amplify the signal and help you to establish the communication. Okay. Instead of amplifying the input signal, if the LNA itself is singing its own song, okay, meaning to say that the LNA itself is oscillating at some frequency. If you demodulate it, you will get one single tone signal which might be in the audio range or may not even be in the audio range. Okay, so there is absolutely no communication there. Like the LNA loses its purpose. Okay, so which is a very, very bad thing. You don't want it to happen. And usually in the industry or even in research, whenever you do any LNA design or any RF amplifier design, you take a lot of pains to make sure that the LNA is stable. Okay. In last class, I mentioned the K delta stability factors, where there are multiple stability factors which you would have learnt in the microwave course. So any of them can be used. And typically what happens is, especially in the IC design industry, the first thing that people look at is, you look at the real part of the Zin. Okay, for your LNA, if you might have designed a wonderful LNA with a very good noise figure and so on, but one of the main things that people look for is what is the real part of your input impedance. Okay, they will plot it across frequency. In fact, when I was working in Qualcomm, like our manager used to ask us to plot it till about 20 gigahertz. Like we were designing my maximum frequency was around 1.1 or 1.3 gigahertz. Okay, and but my manager used to say, please plot the input impedance till 20 gigahertz to see if somewhere at any point in the frequency range it is becoming negative. So for example, at 10 gigahertz, if it's going to be negative, there is a possibility at that frequency the system can start oscillating. Okay, although that is not the intended region of oscillation, intended region of operation, there is a very good possibility that it can oscillate, and you don't want to have any chances of oscillation. Okay, so people take this quite seriously and look at the input impedance. Now, in this topology where we have not even done any input matching, just if you have an inductive load, there is a possibility of the real part of the input impedance becoming negative at some frequency. For example, it can look something like this. The real part of Zin at lower frequencies, it will be very, very high. Okay, and it will fall like this. Okay, and it has to be something like this, and there is a possibility it can go negative also, and it can come out also, but in this region it's basically potentially unstable. All right. Okay, so having said this, we need to make sure that instability doesn't happen, noise figure is maintained, you are able to tune the amplifier. So now you can see different building blocks are coming into the picture, right? So the LNA design becomes more involved. Okay, so what I will do in today's class is basically I will just give you the topology of another LNA. This LNA is actually quite used, I wouldn't say very widely, but it is finding its use fairly well. And the first two other things, whatever we talked about, nobody uses. Okay, so what we will do is in the next class we will continue. Okay, so one of the things that people use is basically to say, I'm going to use feedback. Now all of you know that negative feedback has a lot of advantages. Okay, the only disadvantage is that you have lower gain, but apart from that, we know that negative feedback stabilizes your gain, it extends your bandwidth, it suppresses your noise and suppresses your distortion and a lot of good things, right? So what happens if we use some kind of negative feedback? Okay, let's say this is a feedback resistor RF. Say this is the transistor M1, right? Let's say you have V in RS. Let's just put some DC blocking capacitor. Okay, let's try to find out what is the input impedance here. Okay, and let's say you have a current source to bias this. Okay, now the current source can be implemented as a PMOS transistor which is having a fixed bias. All right, so when you have a fixed bias, what happens? When it is in saturation region, you know that it is pretty much flat. Okay, so in this region it acts as a current source. So this is VDS on the x axis, current on the y-axis. Okay, so what is it for a constant current source? Constant current source, you basically want constant current I naught for all values of V naught across it, right? That is how a current source is defined. If you look at this MOSFET, in the saturation region, it behaves like a current source with some shunt resistance, right? So if you have a certain RS, you will basically see, current which is like this. Okay, so that is what you're having. So you can basically have So there are certain advantages of using this. Let's say you have a feedback resistor. So this topology is what is called as resistive feedback LNA. Okay. In fact, this is gaining a lot of importance. Variants of this is gaining a lot of importance in the industry. In fact, with all this MIMO and things like that, where you have multiple receivers, if you want it to be area efficient, but if you are willing to kind of trade off noise figure, resistive feedback LNAs are very widely used. Okay, so we will look at the derivations related to this this particular type of LNA in the next class. So, but I would like you to, especially those of you who are not very well versed with CMOS, try to draw the small signal equivalent circuit, okay, with only this portion, okay, only this portion, and try to find out what is the input impedance, and we will discuss the rest in tomorrow's class. Any doubts, any questions? Okay. Okay then, so we'll wind up the class now. Thanks everyone. Have a nice day.
Thank you, sir.